Today we are working on Taylor's and Maclaurin series. So we did power series before in 11.9. Suppose f has a power series representation. So we learned how to write a function as some kind of power series in the last thing, right? That's what we did. Now we are here to claim that we are able to find the power series coefficients easily in the Taylor series. So let's say f has a power series representation with center at a. Center a means you're using x minus a in the power series with radius of convergence as r, which is positive. Suppose fx can be written as this power series, which can be expanded to, when I put n0, it will become c0 plus when I put 1, c1 times x minus a to the power 1, c2 times x minus a to the power 2, and so on. And this is convergent. This is convergent if x minus a absolute value is less than r, because r is the radius of convergence. Okay. Now from here, I'm going to be able to try to find c0, c1, c2's values. Okay. So let's see what I do. I differentiate this function IC. I see that f of x can be written as this. What if I differentiate f prime x? What will that look like? The derivative of c naught will be 0. So the derivative of c1 times x minus a would be c1 plus derivative of c2 times this. So 2 comes down c2 x minus a plus 3 comes down c3 times x minus a square, and so on, right? So basically that is n from 1 to infinity. You see n is coming down, cn times x minus a to the power n minus 1. That's what I wrote here, f prime x, right? So what if I put x is equal to a in here? What will that be? Then f prime a, look at this. So if I put f prime a here, this term will become 0, 0. All the other terms will become 0. Only term will be left is c1, right? So that means this is equal to c1. So you can also think of like c1 is equal to f prime a here, okay? Similarly, when I differentiate second time, this, let's try one more step. When I differentiate 2 times, let's say I differentiate this f prime x and differentiate it one more time, c1's derivative will be 0, 2c2 x minus a's derivative will be 1, plus 2 times down 3 times 2 times c3 x minus a power 1, and so on. If I put a in here in place of x, all the terms from second onwards will become 0. It will be 2c2. So basically what I can claim from here is that c2 will be second derivative of f at a divided by 2. So c2 second derivative of f at a divided by 2. And similarly going, you will notice that c3, when I differentiate third time, I get c3, and when I put a in place of x, but in the denominator it will be 3 times 2 times 1. Here it is 2 times 1, right? Here it is 1. So basically I can keep on going and generalize it by induction that Cn is nth derivative of the function at a divided by n factorial for all n values. Okay. Now, also I forgot to mention in the starting that if I just put before derivating, if I put a in here, this will become 0, this will become 0, all the terms will become 0, only will be left c0. So c0 also follows the pattern kind of here. In this thing, which formula we evaluate, Cn is equal to f nth derivative at a divided by n factorial. So when I say f 0, that means no derivative. So basically C0 start with f of a, no derivative of f at a, and then C1 is the first derivative of f at a divided by 1 factorial, and so on. Remember, 0 factorial is always equal to 1. Okay, that also works through. So using our original, you see what I said in the starting. So let's write it down here so you guys can understand. F of x can be written as a series from n0 to infinity, Cn times x minus a the power n. We just figured out that Cn is nth derivative of f at a divided by n factorial. Therefore, our expansion can be written as, in place of Cn, I can write this. Okay. So what will that be? Fna divided by n factorial times x minus a the power n. This is what we have as Taylor series, which is centered at A. Centered at A means all x minus a format. Given a function f which has derivatives of all orders, that means it's differentiable how many ever times you derivate at the point A. You can all differentiate it many times at point A. Then the power series is called Taylor series. This series has a name, Taylor series of f centered at A. If you put a equal to 0, then this is called Maclaurin series. If the series is centered at 0, we call that a Maclaurin series. We conclude, if a function has a power series representation centered at a, then the function equals sum of its Taylor series within the radius of convergence. Remember, radius of convergence means that x minus a should be less than r in absolute value. Okay, so however, there are weird functions which have derivatives of all order but do not equal to Taylor series. We will talk about this later. But let's first learn how to evaluate Taylor series for a given function. We know that Taylor series can be written as sigma n from 0 to infinity f n a divided by n factorial times x minus a power n. So here a is given as 1, the function is ln x. So basically what you need to do is find f of a first. F of a is 1, so that will be natural log of 1 will be 0. F of x is given as what? Natural log of x. What is the first derivative of the function? Which will be 1 by x. So what is f prime of 1? 1 by 1, which will be 1. So c naught is 0. C1 is f prime 1 by 1 factorial, which is 1 by 1, 1. Second derivative is negative 1 by x square. So second derivative at 1 would be negative 1 by 1 square, which is negative 1. C2 will be second derivative at 1 divided by 2 factorial at 2, sorry. So 1, second derivative at 1. Second derivative at 1 is negative 1 by 2 factorial, right? Do you guys notice that the first thing is 0, then 1, then negative? Let's try third one too. Third factorial would be negative 2 come up, becomes positive by x cube. Third derivative at 1. All of them have to be done at a equal to 1. So that's 2 by 1 cube is 2. Therefore, C3 should be the third derivative at 1 by 3 factorial. Third derivative at 1 is 2 divided by 3 factorial. So what is happening? This is 1 by 1 factorial negative. It's alternating series. Let's try one more to figure complete out. Fourth derivative, 3 comes up. This becomes 2 times negative 3, negative 6 by x4. Fourth derivative at 1 will be negative 6 by 1 4, which is negative 6. Therefore, C4 would be fourth derivative at 1 divided by 4 factorial. So basically, negative 6 by 4 factorial. Okay. So let's try to write this in more general formula. Our C naught is coming 0. C1 is 1 by 1 factorial. C2 is negative 1. So you see at 1 there is positive sign, at 2 it's 1. So we can write it n minus 1, okay, in general. So here it is power 1 by 2 factorial. Therefore, I'm generalizing the formula Cn. Look at this. Negative 1 power n minus 1 by 2 factorial. And you guys notice that here we have 2 factorial in the tops, 3 factorial. That's going to cancel. So what we have in the denominator, you see what I'm saying here? This is 1 by 2, right? And here 2 by 3 factorial is going to be 1 by 3. 6 by 4 factorial gonna cancel, just will be left 4. So basically we are left with n at the denominator. This is Cn. So my final representation using this f of x, which was natural log of x, would be equal to sigma n from 0 to infinity and from 1, because c naught is 0. We don't need to write that. I'm gonna write it from 1, negative 1 power n minus 1 by n times x minus 1, because this power n. This is your Taylor series representation of natural log of x. And we can mention that radius of convergence is equal to 1. Okay. And the interval of convergence should be coming out. We can easily do that using our last chapter. That will come to be negative 1, 2. At negative 1, it will not be convergent. At 2, it will be convergent. We can do that using our previous chapters.